Today we will talk about again radiotherapy, but this time we will focus on the technologies used for radiotherapy. So how we use radiotherapy. We saw the theory in the previous lecture. But before going into the technology, let's see what do we treat with radiotherapy. This is a recent paper describing the international situation in terms of mortality, years of life lost, years lived with disability, and disability adjusted life years, the so-called DALY, for different cancer groups. So this gives, you see, the disability adjusted life years, the so-called daily, is the years of life lost, so how many years are lost, plus the years lost due to disability, the so-called YLD. This gives a very good idea of what is the impact of a cancer in terms of, it's much more than mortality, because it includes, you know, the latency, how early the cancer comes, how much it really impacts the life, the quality of life. So you see, in terms of number, you see there were about, in 2017, worldwide, there were 24.5 million cases. Reduced to 17 millions if you take out the skin cancers, you know, and about 10 million deaths. So we are talking about a disease that makes 10 million deaths worldwide. And interestingly, between 2007 and 2017, incident cases increased by 33%, with the lowest increase in the most developed countries. And between 1990 and 2017, neoplasm increased among the top causes of daily from the 6th to the 2nd place. This is something very important. Let me show you first the data on the incidence worldwide. This is the annual percentage age change in percent for the incidence in this map. You see the red is high positive incidence +2, and the blue is the best negative increase, so minus 3%. In the plot below, the same as above, but not for the incidence, for the mortality. So now it's a selection on cancer. Again, red countries are bad, let's say, blue are good. So what do you notice here? First, that the situation seems to be much better for the mortality than for the incidence. You say in terms of mortality, there is a general trend to a decrease in mortality. You see many countries are blue, or even these yellow countries are also doing, they are between minus 0.9 and 0. So there is a slight decrease. Only a few countries are red, you know, like India, Iran, these countries are still red. Actually, Germany is one of the few countries in Europe where the mortality is increasing and the incidence is sharply increasing. The incidence is in the order of between 1.1 and 2%, and the mortality is increasing between 0.1 and 1, while most of the other countries are with about minus 2% decrease. But in terms of incidence, there is a general trend to the increase, both in rich countries, let's say those with high GPD, and in low GPD countries too. You see in Africa, there is a tendency to increase, also in South America, in Asia, in China, there is a strong increase. What is the reason for that? This is different, of course. For low GPD, this is mostly due to the population increase. So we have a larger population, even if this is, of course, it's percentage and it's in age standardized incidence rate. You see the impact of increase in population, and for high GPD country, you see the impact in age. So the population essentially is shifting toward the population more at risk of cancer, because it's moving from a young population to an old population, and then unavoidably you will have more countries, more cancers, because you have a population which is now at a higher risk than it was supposed to be before. For the mortality instead, of course, you see the impact of the screening, so the improving conditions for early detection, and of course the impact of the therapy, so better therapy and early detection, overall lower mortality. So higher incidence because you have increased population and increased the age of the population, lower mortality because you have early detection and and better cure. But a situation which can be drastically different in different countries and in different continents. You see, it depends really on the country and on the continent. What is really nice and really significant is that this is now the daily, so this is not exactly the mortality, it's the sum, let's say, of the year loss plus the disability loss between 1990 and 2017. And this was the situation in 2007. And this is the situation in 2017 in terms of ranking. And you see, this is a very good news, if you want. So in 2007, still, the rank number 1 and 2 were respiratory infections and tuberculosis, and maternal and neonatal disease. Now, both these cause of cancer that are typical of third world countries, you know, typical of the population where the hygiene measures and the protection for the newborns is extremely poor, both are dropped now at the 3rd and 4th place. And other causes like 4th and 5th place here was enteric infections and other infectious disease. They are dropped very low now. They are in the order of 12th and 20th ranking. So this is amazing. If you think about only in 10 years, the world made such a giant leap forward that these diseases that are typical disease of a poor population with poor hygiene condition go down. And of course, the diseases that go up are the typical disease of the rich countries, which is cardiovascular disease and cancer. Because of course, cardiovascular disease and cancer are strongly related to aging, a rich diet, and all conditions that, let's say, are typical of the rich countries. Moreover, being strongly correlated to age, while of course, maternal and neonatal disease are only important, of course, for newborns. Clearly, you see that this means that the overall lifetime of the human population on Earth is very rapidly increasing. Not only the number of people, but also the life expectancy of the people. That per se, of course, is good news. Nobody wants to have a short and poor life. But of course, that's the problem that we are more and more. And then the problem of the pollution, of the climate change, and all this, the main cause, if you want, is always the large number of human beings alive. I mean, that's the main problem that we are facing. But from the medical point of view, this is definitely excellent news. For cancer, instead, the changes are very mild. You see, this is the situation. This was the situation this is not the daily, this is the year life loss, but I mean, similar discussion. This was the situation in 2007. This is the situation in 2017. At the first place, in terms of life loss, so this is more on the mortality side, by far you have lung cancer. Lung cancer remains the main, and we will see also in a few slides. The gastrointestinal cancers are in the second place. Stomach cancer and liver cancer that are not so common in the West, but quite common in Asia, for example, are still in the second and third place. Colorectal cancer, which is very high also in the West instead because of the diet, fourth, remained fourth. Breast cancer is the first cancer among women, but is the 5th place overall, because of course women also have these other cancers. And then you see that there are no big changes. Maybe among the most important change, there is pancreatic cancer that goes from the 9th to the 7th position, and that's because the cure for pancreatic cancer is still completely missing. So while some cancers are going down, like brain cancer, cervical cancer are going a little bit down, pancreatic cancer is going up because you have no cure for pancreatic cancer. And in here you can see essentially how is the ranking. I mean, from the most, keep in mind that for men, we will see in a second, don't mix mortality, years life loss with incidence. Prostate cancer, for example, is very prevalent in the Western population, very prevalent. It's the #1 cancer in men. And it also has a relatively high mortality, we will see in a moment, but the year life loss takes into account the how early the cancer comes. So, and prostate cancer typically comes in men over 70 years old, which means that the years life loss compared to the average life are relatively small, not so many years. If you compare to cancers like, let me see, like leukemia, which is down here, which is extremely rare, but can occur in young people. So you have a high, you see them in the, of course, not all cancers are in the ranking because you can have cancers everywhere. Leukemia is relatively rare, but you see it here because of you have a lot of life loss. Same also for brain cancers. There's a lot of brain cancers in pediatric that, of course, increase the years of life loss compared to the absolute incidence. Acute lymphoid leukemia also, same problem here. Now, if you look at this is Globocan 2018, this is the same, but it's a different paper on Cancer Journal for Clinicians, but so this is overall in the world, the total incidence, a little bit easier to understand. This is the total incidence and the total mortality. And you see that for incidence, worldwide, of course, not specific to the country, but worldwide, lung, breast, and colon are very close, and prostate, let's say. Lung, breast, colon, and prostate are very close. These are the 4 main cancer in terms of incidence. And in terms of mortality, too, you see that lung and colon, lung is by far the first here, because among these 4, lung is much more lethal than breast. You see, breast here is almost 12%, here is only 7%. And colon is still pretty much a problem, but you see prostate, for example, drops down here. And while instead you see pancreas, you don't see it at all in this pie graph here, because it's here together with the others, but you see jumping here at 4.5% because essentially the mortality is the same as the incidence. Incidence and mortality are almost the same. Esophagus, you see, is also quite prevalent, but especially in Asia. This is a nice plot because this gives you in this color code, you see which is the most common cancer. This is incidence, not mortality. The most common cancer in different countries in the world. Top panel is males, and bottom panel is females. So now you see clearly that for males, the green color is prevalent, and the green color is, of course, prostate. You see Europe, United States, Africa, especially Central and Southern Africa, Australia, prostate by far. The blue color is prevalent here. This is lung. You see, if not, apart from prostate, the lung is also fairly common in many countries, like in Russia, in China. These are mostly countries where the non-smoking policy is not very effective. So for these countries where you still have a relatively high incidence of lung cancer, this is due to poorly effective smoking policy. So you have it in Russia, you have it in Asia, and you have in some countries in North Africa. In a few other countries, like in India, oral cavity, or in some African countries, you have liver. These are countries more due to the hygiene conditions, to the water. Liver is very much correlated to the water. For women, by far, you see, in terms of incidence, the number one is breast. There are few exceptions, as breast is essentially everywhere. With few exceptions, you see, like in Korea, where interestingly thyroid is more common, and in these orange countries that you see a little bit in Africa, South America, and Asia, this is when the liver is prevalent. Otherwise, breast is always prevalent almost everywhere. And this is mortality. Now, of course, as I told you before, there is a clear shift between incidence and mortality, because, of course, now lung, that was still very high, especially in the east part of the map. Now it's a little bit everywhere. The number one, by far, is the number one everywhere. In Africa, there is still a lot of mortality for prostate, because here is probably due to the fact that there is not enough screening and not good enough cures. And in India, the head and neck tumors are still prevalent, because the head and neck tumors also have a relatively high mortality. For women, you see that breast is also the higher mortality in many countries, but not everywhere. In some European countries, lung is prevalent. Also in United States and Canada, lung is prevalent, and in the southern part of Africa and some Asian countries, liver is the main cause of mortality. This is only for United States. A little bit more in details. Male and female incidence and mortality. This is 2019. So these are the new cases expected in 2019, and for male and female. Again, United States, prostate for men and breast for female, but lung is at the second place and colon is at third place for both. Fourth place is the bladder for men and uterus for women. In terms of mortality, instead, the first place always lung, second place the one in the incidence, prostate and breast, third place colon again, and then you see the fourth place of pancreas, which is surprising again, because this is pretty low in terms of incidence, but becomes pretty high in terms of mortality because of the very poor cure rate. And this is how the rate, this is the incidence, develops with years. It's a plot that goes in United States from 1975 to 2015 for men and women. I think this is quite interesting. You see, prostate, here there is a huge peak, and then there is even a decrease here. But this is really a diagnosis bias. At about 1985, it was introduced the PSA measurement in the blood, the prostate-specific antigen measurement in blood, which allows, of course, a very easy screening of the prostate. So you have a peak here, which has then been adjusted when it was clear that PSA was kind of over-diagnosing prostate cancer. What is really interesting instead is to see that in both male and female population, the colorectal cancer is decreasing, probably as a result of a better diet habits in the, let's say, in the 90s and the 21st century compared to the 70s and the 80s. And the lung is also drastically decreasing in men, but unfortunately, now it is decreasing also in women, you see, but it was more difficult for women because while there was an aggressive campaign for quitting smoke that was well received by boys. It was not always well received by girls for many years. I think now it's happening. You see here, there is a first sign. There is a first sign of decrease also for women, because you start to see less girls that smoke. Okay, now let's go to radiotherapy. Now we have this introduction to cancer. What about radiotherapy? Now, of all the cancer patients that you have seen before, the cancer patients means the incidence plot, not the mortality plot. Of course, mortality is important, as you can imagine, but the cure applies to all patients in the incidence graphs. About 50% of these patients will need radiotherapy. It's somewhere between 50% and 60%. Now let's look at Europe. In Europe, there are not enough LINACs. We'll see what is a LINAC in a second. Not enough radiotherapy machine, with the result that about 1 in 4 patients in Europe do not have access to the needed radiotherapy treatment. These are plots you see of the, again, only for Europe and not for every country in Europe, only for the countries where the data are available. These are the megavolt units. If you want, we will see in a second what is a megavolt unit, what is a radiotherapy unit per million inhabitants. And these are the megavolt units for 10,000 radiotherapy indications. So for that 50% of the cancer patients that need radiotherapy. So as you see here, some countries in Europe are doing much better than others. It's kind of expected. You see that Scandinavia, Denmark, also both in terms, if you normalize to the inhabitants or if you normalize to the mortality, that Scandinavia is doing very well. But maybe you will have noted already, it's a bit surprising that Germany is not doing so well. You see, if you normalize to the population, Germany is doing worse than France or Switzerland. And if you normalize to the people that need radiotherapy, so to the cancer cases, is doing even worse than other countries like Italy, Spain, Austria, is really not doing very well. What is the meaning of this plot? The meaning is that in Germany, you need more radiotherapy units, and then you need more medical physicists, because of course, medical physicists are essential. Every time you have a radiotherapy unit, you need a team, not only one, you need a team of medical physicists doing the treatment planning, the quality assurance, the dosimetry. So you can be more than sure that if you want to do medical physics, you will find a job in Germany very easily if you look at these plots. I mean, maybe less easily if you are in Norway or in Finland, where actually there are a lot of radiotherapy units already. But in Germany, you definitely have to increase the number of radiotherapy units. So there are different types of tumors. This we'll see in terms of radiosensitivity. Some are more radiosensitive, like lymphomas, germ cell tumors, small cell carcinomas. Others are more radioresistant, like melanomas, sarcomas, glioblastomas. But for the technology point of view, we have essentially 3 types of radiotherapy. We have the external beam, the so-called teletherapy. We have the brachytherapy, which is instead internal, and we have the systemic radiotherapy. We will not touch the systemic radiotherapy. Systemic radiotherapy means that essentially you give a radionuclide and you let the radionuclide go to the target. In most cases, this is done for palliative reasons. So to target, like if you use strontium, you do it to target the bone metastasis. In other cases, like for iodine or radiolabeled antibodies, this is curative, but we will touch systemic radiotherapy when we will talk about nuclear medicine. This is more about the use of radioisotopes in medicine. In this lecture here, we will focus on brachytherapy and teletherapy. Brachytherapy, brachy means short in Greek, so essentially means that you use is a therapy that uses short range isotopes. This can be done by contact therapy using really plaque that go on the tumor. This is of course in case of skin cancer, but also for the eye, you can use this plaque. Or you can have interstitial therapy, which means that you actually implant radioactive seeds or wires in the tumor. Or can be intracavitary in case you have hollow, in case you have a hole, so you can actually insert your needle in the cavity, and this is the case, for example, of the uterus typically, but also in principle of the mouth, of the esophagus, every time you have this. Which are the typical isotopes used? Typical isotopes are these shown here, from radium to cobalt, cesium, gold, and these other here. This is the half-life that you see is markedly different. Some of them is extremely long, some of them is relatively short. And this is the typical application in clinics. I mean, some are temporary, for both intracavitary and interstitial. Other can be for contact, and other can be permanent. Permanent means that essentially you implant the needle interstitially and you don't take it away anymore. You just leave it there. So examples of interstitial, you see, you can have this. This is a case for, of course, the problem of brachytherapy, especially interstitial brachytherapy, is that it's very invasive. Essentially, you have to invade the tumor and shoot the needles with this kind of devices in the tumor. While for intracavitary radiotherapy, this is relatively easier because you have the cavity, so you can enter and then you can deposit the needles. The treatment plan, now this is a color palette. I'm sorry, I should have shown you before the teletherapy, let's say, so you understand better the color palette. You see that the needle is shown here in the CT, and the color palette corresponds to the doses. You see it goes from 14.5 grays, green, 10 gray here, and then this is an area of low dose. The big advantage is that you can give a very high dose with a very short range, in the sense that because it's limited by the range in tissue of the isotopes, after a certain range you stop, and the range can be extremely small, so you can spare completely normal tissue if you use brachytherapy. The disadvantage is that, of course, the dose is very non-uniform, because of course if you are closer to the radioisotope, you will have a higher dose than if you are far away. It's impossible to have a very uniform dose. So you have a gradient of dose. If you want to have a more uniform dose, for a large tumor, you should implant a lot of seeds, which is not nice because it's very invasive. So for this is another example. You see intracavitary in the esophagus, which is something I will not be happy to do. So I will not say much more about brachytherapy. The use of brachytherapy at the moment is quite limited. It's still used for cancer. Also, it's used for anal cancer. Sometimes it's used for uterus cancer, as I said. But the problem of the invasiveness and the problem of the relatively small, relatively dishomogeneous dose makes its applications difficult. Much more used standard is teletherapy. Teletherapy, which is instead completely non-invasive, because now the beam comes from outside. I don't touch the patient. I don't touch in any way the patient. The problem of X-ray therapy, let's say, that was immediately, I mean, shortly after Röntgen discovered X-rays, it was clear that it could be used to treat lesions. But the problem is the depth dose distribution. So if you have a tumor at a certain depth, you see, these are organs at risk here. This is the liver, these are the kidneys, this is the spinal cord. If you have a tumor here and you shoot the beam and you take an X-ray machine and you shoot the beam in this direction, the dose here will be higher than the dose to the tumor. And then you will, of course, you will also have a tail, because, you know, the X-ray don't stop, so they go down here. So how do you fix this problem? Well, you use more beams. You see, even using only 2 beams, now you have a higher dose here, like 100% of the dose here. You have 60%, 60% here, 40%, and 40% here. So you see, here is the example of using 2 beams that cross in the tumor. Of course, the idea is that you have this crossing of the beams on the tumor, so they overlap in the all beams have to overlap in the tumor region in a way that you will have a higher dose to the tumor than to normal tissue. So that's why we do teletherapy. Other with photons, I mean, we will see with charged particles is a different story, but we have already seen in the physics part. But with photons, you have to live with the physics. There is nothing to do. But this shooting in overlap is the trick to do radiotherapy. And these are the color palette that the medical physicist has to do. This is the treatment planning system. Essentially, this is now is not full in color as normally is only done with the limit. Essentially, what you would like to have, you will like to have everything red, 100% of the dose. So the therapeutical dose is here. You would like to have something like in brachytherapy if you want, so that you have all the dose here and no dose in the normal tissue. But this is impossible. This is impossible because if you have teletherapy, you need more beams, and then you will have you see these other colors correspond to 90%, which is here, of course, in the around the crossing of the beam, you will have 90%, 80%, and then you have also in the entrance channel, you have 70%, 60%, 50%, and then these blue regions are 20%, 10%. But you see, for a treatment of a prostate like here, you have a large volume irradiated. Lot of organs are irradiated around the prostate, even though, of course, there is even lower dose than the tumor. So the old method for treatment was the so-called 3D. I mean, the old method was really just shooting the beams, but for many years, let's say in the 20th century, the method was the so-called 3D conformal radiotherapy. How do you do 3D conformal radiotherapy? Essentially, you irradiate generally in a box. So you shoot, let's say, in anterior posterior direction and in the lateral direction, and you shape the beam with these collimators, which are really individual compensators, still used in some cases. We will see today is more used the MLC, the multi-leaf collimator, is that, which is like a compensator, but you can change because you have a lot of leaves, metallic leaves, of course, that you can move. But these were shaped based on the imaging, and you can shape it for the tumor, and then you irradiate, and the compensator will stop the beam and will only let go the beam in the area, in the volume that you want. But this technique has been now almost completely abandoned. There is very little left because it's been replaced by IMRT, intensity modulated radiotherapy. The idea of IMRT is that now you don't irradiate everything with the same intensity. Essentially, you irradiate from many different angles and with different intensity. So when you have an organ at risk between the entrance of the beam and the tumor, you give a low intensity, and then you compensate it with a higher intensity in another part, in another angle. So you use many angles and different intensities. The result are like this. You see, this is a complicated tumor because it's a base of the skull tumor around the spinal cord. You see, the spine is here, so you want to spare it. But you see, the conformality is very good, even though there is some dishomogeneity, because of course you have hot spots and cold spots due to the different intensity. And of course you irradiate a very large volume, but essentially you can be very conformal. This is shown better here. You see the impact of the crossfire. You see here, let me see, maybe I will restart. This is, so let me see from here. In the movie that you will see the irradiation from many different, this is actually an arc therapy. We will see later what is an arc therapy. So you irradiate under almost every angle. And at every angle, you see in the first plot, you see the cross-section of the tumor from that angle. In the second one, you see the depth dose distribution for that angle. And the third one, you see the integral, the sum of the depth dose distribution. When you see the cross-firing, the advantage of the cross-firing. So you see here, every time you shoot, the tumor is a prostate in the center, the dose is higher here than here. But if you look at the integral now, you see the sum of all these beams, then magically you see that the central part gets a much higher dose than the normal tissue surrounding, even though the normal tissue surrounding with this arc therapy is which is the product, if you want, the dose times volume, because the volume is very big, you have a very high integral dose. But you see, I think it's quite nice in this plot how this bad depth dose distribution with the trick, and you see with the change of intensity, because the intensity is always different, and the cross-firing from many different angles, you get a very nice depth dose distribution at the end. So this is, for example, a comparison of 3D CRT and IMRT for different tumors. This is for esophagus cancer in the transversal and sagittal views. 3D CRT, you see, is a box. Of course, with the compensator, you can do a little bit better, but with IMRT, clearly you do much better. And this is for prostate, you see the 3D CRT and the IMRT, and this is for lymphoma, 3D CRT and IMRT. So you clearly see that you are much more conformal, and so, but not necessarily you spare more normal tissue. For if you look at lymphoma, for example, you actually irradiate more normal tissue here than doing 3D CRT when you irradiate a lymphoma. You know, a mediastinal lymphoma, where you have to irradiate the lymph nodes on in the mediastinum. I'm sorry, the mediastinum. Okay. This is now the dose volume histogram for a comparison of IMRT and 3D CRT for non-small cell lung cancer. So for the general, the type of lung cancer treated with radiotherapy is the non-small cell lung cancer. And you see the clear advantage that you have moving from the dashed line 3D CRT to the thick lines that is IMRT. The coverage of the target with 3D CRT is necessarily poor, because you cannot go so high with 3D CRT, because you will have unacceptable toxicity. But still, you see that the toxicity in the heart, in red, in the spinal cord, in the esophagus, and in the whole lung are generally worse with 3D CRT. Not always, if you look carefully. You see, for the whole lung, for example, there is practically no difference. And for the esophagus, depends on which volume of dose you are talking about. So not always is that. But you do also much better with the lymph nodes. If you want to spare the lymph nodes, you see here that if you compare the 3D CRT, which is dashed with IMRT, either the normal IMRT or the MRT, with marking the lymph nodes as organs at risk, you see that you can do much better. So how do we do radiotherapy? This is the radiotherapy chain. So this is very important to remember. The first step is always imaging. The second step is segmentation. Then you have the treatment planning, the plan verification. So this is all without patients, except for the imaging. You do imaging, then you do segmentation, treatment planning, plan verification, patient positioning, and finally treatment delivery. So you see imaging, segmentation, treatment planning, plan verification, patient positioning, treatment delivery, and finally you have the verification of what you have given. So you do a post facto dosimetry if you want, and and test, and then you repeat patient positioning and treatment delivery. You generally don't repeat here, even though in some cases, especially modern radiotherapy, you can go back to imaging and to treatment planning. For example, if the tumor shrinks, and then you have to replan. If you are afraid that there are intrafractional movements of the tumor, then somehow you have to go back to the whole chain. But the whole chain is very slow, still too slow. So people prefer to do it once before the treatment, and then you fractionate how much you can fractionate, and then you only repeat this phase here. Now, imaging, we will have a dedicated lecture on imaging, but the basis of imaging is the computer tomography. It has been said many times that CT is the most important innovation in radiotherapy since Röntgen. So after Röntgen comes the Hounsfield with the CT, because imaging has completely revolutionized radiotherapy, because of course, now you can see properly in 3D what you have to irradiate. Before CT, you can only see in 2D. Now you can see in 3D, and this has changed radically. These days also MRT, magnetic resonance tomography is very much used, especially for the soft tissue tumors. You see, this is brain tumor visualized in MRT. You can see it much better in MRT than in normal CT, even though very often you use both. This is a comparison of a brain tumor you see in CT and in MRT. Now comes the phase of the segmentation. What is segmentation? Segmentation, you have to do two things. You have to define the target volume, and you have to define the organs at risk. In 90% of the cases still today, this is done manually, but there is a tendency to go into an automatic segmentation based, however, not on simple software, but more based on artificial intelligence approach, so that the computer does the segmentation. But at the moment, in most cases, this is done not by the medical physicist, but is done by the radiation oncologist. So the medical physicist only gives the CT to the radiation oncologist. The radiation oncologist makes the segmentation, you see, so segmentation of the target. We will see that this is not so easy because there are three targets: GTV, PTV, and CTV. We will see this in a second. And most important, segmentation of the organs at risk. You see, in the case of tumors in the head and neck, these are images of tumors in the head and neck. There are many organs at risk in the head and neck that the clinician has to circle, and the medical physicist will have to consider them as organs at risk and try to spare them as soon as possible, or at least to spare them according to the maximum tolerable dose for those organs at risk. The target volumes, as I was saying 1 minute ago, as defined by International Commission of Radiological Units into different issues, are the GTV, which is the gross tumor volume, which is essentially the tumoral mass; the CTV, the clinical tumor volume, which is a tissue that contains a demonstrable GTV, and/or clinical malignant disease that must be eliminated. So the CTV is the GTV plus a margin. And the margin is due to the fact that you assume that there is, you see, even when you see this nice tumor here, you assume that there is some small disease which is out of the margin. You cannot see it in the imaging, but you will see it, for example, in histology. And finally, the PTV. The PTV is again bigger and takes into account many other factors that are not related to the biology of the tumor, but are related to the technology that you use. For example, the movement of the tumor, the intrafractional movements, the precision in positioning. So you want to add another margin to make sure that you are in. So at the end, you have a situation like for a lung, you can have a situation like that. You see, well, you have the GTV is red, the tumor that you see in the CT scan. This is a transversal view of the two lungs, and the tumor is very clear here. The CTV takes into account, you probably see them, this kind of infiltration of the tumors, But the PTV is much, much bigger because, of course, there is a movement here in the lung. So you want to give eventually the dose here. The medical physicist will consider the PTV as the region where you want to give 100% of the dose. Actually, if you remember the dose volume histogram, you want to give, let's say, the V90 minus V5 must be 99% of the volume, of the dose. I mean, of course, you will have a kind of decrease, but the message is that that is the target. But keep in mind that going from the GTV to the PTV, you are irradiating normal tissue, essentially. And this means that you will have toxicity. So if you increase your margins to have more confidence, you will pay this increase in terms of increased toxicity. And then you go to treatment planning. Treatment planning, which is now the mathematical procedure that you have to do to create the depth, to decide the angles and to decide the intensity around the angles. This can be conventional and the inverse. There will be a dedicated lecture on how to do treatment planning, and you will also use a software for doing the treatment planning. Most important for doing a treatment planning is what is the limits that you have, and this come from the organ-specific dose tolerance that come from one of the most appreciated reports still used, this so-called Quantec report, which is published in the so-called Red Journal, which is the journal of the American Society for Therapeutic Oncology. These are 16 organ-specific papers, like you see. For spinal cord, for example, you have a number of recommendations like this one, limited toxicity data, standard way of contouring not entirely settled, but in most cases the spinal canal is contoured, not the bones, the canal. No? The use of safety margins around the cord, too useful in practice, may add to the confusion. The alpha-beta ratio is low, 0.87 gray. This is important. So the spinal cord is a low alpha-beta organ, which means a fractionation is very useful for the spinal cord. Other kinds, here you see a study on the parotid glands that are typical side effects in head and neck tumors, where because you have reduced salivary function, you have xerostonias, alterations in speech, nutritional problems, it's pretty bad, you see. And this is the TD50, so the dose that gives 50% of the effect as function of the follow-up durations. For parotid flow reduction, for example, 30-45 gray is the TD50. That gives an effect in 50% of the case. You see here different values. There are NTCP models that are used and explained there. And what is important here is that at the end, like in this specific case for dysphagia, the data are given as dose volume data. So this is what you remember from the dose volume histogram. So you have 60 gray for a V50 of 50%, 66 gray for a V50 or 80%, and so on and so forth. So it's a combination, of course, of doses and dose volume histogram. This is the mean dose, which is also an important parameter for the lung as a function of radiation pneumonitis for different studies. You see, there is a lot of scatter in this data, but essentially you see that this is the probability of pneumonitis and the mean lung dose. Keep in mind that you would like to keep the general rule, I forgot to tell you, this is important, you would like to keep the toxicity below 5%. The magic number is 5%. Generally, you want to have NTCP like here, you see, 5%, which correspond to a mean lung dose of something like 7 or 8 gray. If it is possible, I mean, in many cases, you accept a higher risk like 20% because there is not much you can do. You have already seen in those volume histograms, sometimes it's almost impossible to go to 5%. Then after the treatment planning, you have the patient immobilization. Immobilization is important, especially, of course, it's essential when you have like head and neck or brain tumors where it can be, there is no movement here. So you can actually, the immobilization is very strong. You do your better, of course, to immobilize also for the abdomen, but there will be movements for chest and abdomen. These things are generally compensated in simple ways like breath hold. So you ask the patient to hold the breath and then you give the beam. Then the patient breathes, then hold the breath again, give the beam. This is used a lot for the chest and for the breast. And abdominal compression, as it is shown here, for the abdominal tumors, because the abdominal compression reduces the movements. But then there are more sophisticated techniques for handling the movements that we will see. Now, what is the equipment for this treatment, for the beam delivery now? Let's go to the beam delivery. So you have different kinds of X-rays. 10 kilovolt peak to 150 kilovolt peak is called superficial. Up to 400 kilovolt peak is called orthovoltage. Then you have radioactive source, essentially cobalt, also cesium, the so-called gamma ray therapy. And then you have megavoltage. So in the past, all these were used. These days, there is still some use of low energy electrons more than low energy photons for superficial tumors, but then all the other deep tumors are treated with LINAC, with megavoltage. So superficial, this is superficial treatments. You can read the slide with some detail, but essentially this is the orthovoltage. You see, these are all old images. The cobalt, which actually when I started to work in this field, there were still a lot of cobalt machines, and still there are some cobalt machines, especially in the third world, because they are relatively cheap because you see here the gantry already also with the cobalt. Cobalt is a source, you see it here. Okay, so this is there is a source, and then you move the source and you deliver the beam, but you can rotate the beam around the patient so that you can irradiate from different angles. So this was common, but now you have the LINACs. LINACs are actually linear accelerator of electrons. Then they hit the target, generally in heavy metals like tantalum target. And from the bremsstrahlung, you produce, this we have seen in the physics already, you produce the photons that then irradiate the tumor. And these objects rotate around the patient so that you can irradiate from different angles. This is a little bit more the detail of the accelerator. There's a microwave wide, the klystron. We will see why in a second. This is the gantry, so that's the part that rotates around the patient. And this is the accelerator of waveguide. So the accelerator, of course, you need the vacuum pump to make the vacuum. The electrons are accelerated here. They are bended by a magnet here, and then they hit the target. And from here, you will have emission of X-rays of the patient. Then you rotate the whole thing, which is heavy and massive. You have to rotate it around the patient to irradiate in different angles. So what are the principles of linear acceleration? Well, this starts, this is a very old story already in the 30s. Videroe invented this drift tubes, where essentially the idea is that you have a potential difference between the different tubes, an electric field, so that the particles are actually accelerated between the different tubes. But what is the idea? The idea is that if the length of the tubes increase with the particle velocity, so you make it longer and longer during the acceleration, such that the time of flight is kept constant. So you have to keep the time of flight constant here, which is a problem because, of course, you have to make it longer when they are faster. And is equal to half of the radio frequency period that gives the potentials. Then you can have a synchronous acceleration voltage. and experience an energy gain delta E equal to Q delta V at each gap crossing. So keep in mind, you have, so you have a radio frequency here, and you modulate the radio frequency in a way that the time of flight is constant. So with the constant frequency, you always accelerate the bunch of particles from one tube to another. Very simple compact. Of course, the result is that you have a bunched beam. And these are the basic equation. Let's say the delta. This is your radio frequency that gives you the voltage as a function of, this is the maximum voltage, and the cosine as a function of the time, and this is the omega, the frequency of the radio frequency, and this has to be the condition. The delta E must be equal to this one. So more here, I'm not going into many details. The basic law that you get is that if you want to have synchronous acceleration, if you really want to have synchronous acceleration, this is the condition that you have to do. The nth drift tube, the drift tube number n, must have a length which is given by 1/2 beta n. So that's the velocity in the nth drift. And this is the wavelength of the radio frequency. If this is the condition, then you will have an energy gain per unit length, so the accelerating gradient, which is given by this formula. Essentially, you see it's proportional to the maximum voltage of the radio frequency, inversely proportional to the wavelength and to the velocity. So essentially what happens is that if you see this, if you want to keep the length shorter, definitely shorter than the radio frequency, you need to keep a low velocity, and the average accelerating gradient increase pushes towards small lambda. So essentially, the idea here is that if you want to go higher, you have to go to high frequency, very high frequencies, and this can be done using this, enclosing the system in a cavity with the resonant frequency that matches the radio frequency of the generator frequency. Doing this way, you can go to extremely high energy linacs. This is, for example, already in '66, the Stanford SLAC, the accelerator, linear accelerator in Stanford in US, that is a 20 GeV electron. We don't need 20 GeV electron for therapy, but I wanted to show you that if you use a magnetron at 2.856 megahertz, then you can go up to up to reach 20 GeV, but now goes up to 50 GeV, but it's 2 miles long. Of course, you pay this, it must be very long if you want to have these energies. And you use this accelerator to discover quarks in 1968. The accelerators for particle therapy are, at the moment, there are no linear accelerators. There's a lot of effort in doing linear accelerators, also for hadrons, for protons and heavy ions, but at the moment we use only cyclotrons or synchrotrons. Cyclotrons have a fixed magnetic field and a spiral trajectory, and the energy is given by the Lorentz force, essentially is proportional to the magnetic field and to the radius. Synchrotrons instead are fixed radius, so they move, the particles move along a fixed radius, and then of course you have to have a change in magnetic field. To have a synchronous movement, you have to satisfy this condition. And you see here in the synchrotrons in particular, to overcome the limits that you have in the cyclotrons, you have to keep the beam circulated a fixed trajectory, which means you see that this law has to be satisfied for the radius. So the radius, which coming from the Lorentz force is the P over Q 1 over B, this must be constant. You see, because the particles move here. To do that, you see, you have the bending and focus magnets here in the accelerator. And what you do here, you increase the bending magnetic field at a constant rate. So you inject the particles from here, then you have an acceleration here, and then you have a flat top, and then you extract. And then you repeat, you go down so you can inject again, and then flat acceleration, 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 because you have an increasing magnetic field, then you have a flat top, extraction, and so on and so forth. Okay, this is of course for the linear accelerators that we use in radiotherapy. The energies are involved not GV,
exactly as they were in their CT scan, where the doctor planned out where they're going to treat. So the doctor
if you watch this movie for a second,
scan, and they get all their planning done, and then they come in here and we position them on the bed here in whatever treatment position they need. So, for example, if you're getting breast cancer treatment, we'll have their arms up in the air so that we can position them with their breasts in an open position. And we give them little tattoos for positioning. And we have 2 lasers in the walls here and 1 in the ceiling. And they create sort of a crosshair, if you can see. And what we do is line the tattoos up right into the crosshair of that laser. And that ensures that the patient is in the correct position every single day. So once we have them in the perfect position, there's 2 arms on either side of the machine here that come out, and they enable us to take daily x-rays of the patient. So every day we can take an x-ray that shows us their bony anatomy, so that we know that they're in the exact same position every day for their treatment, and we know exactly what we're treating.
To make sure
so
that
once
there
they're
are no
in the perfect
major
position, we can start the treatment. The radiation comes out of the head of the machine here, and this can rotate around in any direction to achieve whatever angle necessary. So you can see the table rotates, and it can go up and down. So there's a light that comes out of the head of the machine here that shows us exactly the area that we'll be treating. So this light will be illuminated on the patient's skin so that we know, we can visually assure that we are treating the correct spot. And inside of the head here, there's hundreds of little lead leaves. You can see that move in and out to create any shape necessary to treatment. No 2 tumors are exactly alike, so these leaves enable us to be very custom for each patient. So in the light field here is the area that we're treating. In the gray spot here, we could save healthy tissue or protect critical structures from getting too much radiation while still delivering 100% of the dose to the areas within the light field here.
Okay. So, now let's go a little bit 1 step ahead. Let's go to radiosurgery, which is now a little bit the new frontier. In radiosurgery, also called stereotactic radiotherapy, what you try to do, you want now to reduce the number of fractions and to increase the dose per fraction. So you want to do short treatment. This has many advantages. As you can imagine, that there is an obvious advantage for the patient that he has to come less times. There is an advantage for the repopulation of the tumor, because you will reduce repopulation if you shorten the time. Remember the Fowler formula with the time factor in the BD. And there are 2 types of radiosurgery. One is called SRS and one is called SBRT. SRS is the stereotactic radiosurgery, which is used for cranial lesion. SBRT is a stereotactic body radiation therapy, is used for body lesions. So for SRS, the most common machine is not a LINAC, but is a gamma. It's called the gamma knife. And this device, you see it here, consists of 201 cobalt-60 sources of approximately 30 curies, each positioned in a device so that the radiation beam converge at the specified point of treatment. This is only for brain tumors, you see, and you can see how the machine is done a little bit more. This is the helmet, and you go into this shielded area here, and the patient positioning collimator is here. And this gives very high dose to brain tumor with essentially no movement of the patient. However, if you want to go to the body to treat lesions in the body, then you go to tomotherapy, where essentially you see it here. You have a rotation, you move the patient like in a CT scan, and you have a helical rotation because you move and you rotate. So you have a helical irradiation here of the patient. This is called tomotherapy. It's a continuous helical irradiation. Or you have VMAT. In the VMAT, the patient is not moving. It is the LINAC which is moving essentially continuously around the patient. VMAT is generally faster, but for complex structure like in the head and neck, where you have very complex tumors, you have to do multiple passages, and then at the end, tomotherapy is preferable to VMAT. But the two techniques are similar. They both have this complete rotation around the patient. The third one is the CyberKnife. In the CyberKnife, you really have instead is the accelerator which can move actually in the complete space in 6D if you want, because it can move in the space and can rotate completely. You see, it's a head of an accelerator, and can also provide very, very high doses, and is particularly useful when you have moving targets, because of course the accelerator can synchronously move to irradiate the moving target like a lung, when you have a large movement, and the accelerator can move to irradiate the moving target, while this is not possible in VMAT or in tomotherapy. That's how the treatment plans look like. You see, this is for a hepatocellular carcinoma for the liver, IMRT, VMAT, and tomotherapy. Tomotherapy looks good, but you see the dose buff. I mean, the integral dose in tomotherapy is always quite impressive. You see. I'm sorry, the hepatocellular carcinoma is down here. This is, of course, is non-small cell lung cancer. It's a lung tumor. This is the hepatocellular carcinoma, and this is CyberKnife. This is VMAT with active breath control. So the patient is asked to hold the breath. This is tomotherapy, where you don't use any compensation for the movement. And this is VMAT with abdominal compression. So you see the different treatment plans that you get with the different. There is actually sometimes you put a threshold in the dose where you don't show other dose which is still received by other organs. And so this is for the hepatocellular carcinoma. This is also hepatocellular carcinoma with IMRT, VMAT, and tomotherapy. You see in the tomotherapy you have quite a lot of those received by the patient. But why this works? Because we saw that fractionation is essential, but the problem is that parallel organs respond approximately according to the mean dose in the tissue or organ, and the mean dose is much lower than the tumor dose. So therefore, the radiobiological effect is less that it can be indicated by the BD when you use a alpha beta of 3 gray, a relatively low alpha beta ratio. Furthermore, the more conformal is the treatment, the lower is the mean dose relative to the tumor dose. So this is a nice example here. This is now a calculation of the NTCP for two organs, one a typical parallel organ, the lung, and one a typical serial organ, the esophagus. And this is calculated with CRT, so with 3D conformal radiotherapy and tomotherapy. This is not really AMRT, it's tomotherapy. Sometimes you use the same word, but the meaning here is tomotherapy. So look, if you take this green curve, this is esophagus in CRT. And if you take this purple curve, this is esophagus in IMRT. So you see in both cases, for all number of fractions, this is the number of fractions, this is the NTCP. For both number of fractions, for all number of fractions, IMRT is doing much better than 3D CRT in treating this is a non-small cell lung cancer. But you see that when you reduce the number of doses to the lung cancer, the NTCP explodes, which is something you know. If you take corresponds very nicely to the biological effective dose, to the Barensen formula, if you want. No, if you increase the dose per fraction, this is what will happen. This is what will happen. You will largely increase the NTCP, and because the alpha beta ratio of the normal tissue is lower than the alpha beta ratio of the tumor, you will have a large increase here. So to have the same effect in the tumor, this is the NTCP calculated for the same effect in the tumor, you go to unacceptable toxicity for the serial organ. But you see for the lung, here in red is the 3D CRT and in black is the tomotherapy. Again, 3D CRT is always worse than tomotherapy, but if you reduce the number of fractions, same BD in the tumor, surprisingly, you don't have any large increase in toxicity, except when you go to very, very little fraction. And even here, you see, if you use tomotherapy, the increase is not so big. I mean, it's much bigger if you use 3D CRT. So you see that essentially for parallel organs that responds with the average dose, the toxicity remains low even at small fractions. So actually you can do it. You can go into SBRT. And that's what in fact people does. And you see for the stereotactic, of course, in stereotactic radiotherapy, you must have systems like tomotherapy or VMAT, you have to, or CyberKnife, you have to rotate about the patient. Imaging is essential. And motion has to be compensated as much as possible, for example, with abdominal compression. And the other thing is that you have to accept, if you want to give this treatment, you have to accept an heterogeneous dose distribution. So if you want to reduce the time, you want to give more than 100% to the center of the tumor, something like 150%. You see, somehow the thing is shown here. This is the difference in dose fall off for SBRT, as shown here, and conformal radiotherapy, as shown here. So with an inhomogeneous dose distribution in the target, a rapid fall off outside the target can be created. While in conformal radiotherapy, a homogeneous dose distribution inside a larger PTV, so you take a larger PTV, results in a slow dose fall off outside of the target. So in SBRT, you have to take small margins. You have to reduce the margins. You cannot take margins too big. And to have a rapid fall off, you want to have a dishomogeneous curve, dishomogeneous dose distribution with an overshoot. This is, I don't know if even my colleagues appreciate how important this was revolution, that happened at the beginning of the 21st century in this field. We dropped the dogma of the uniform dose. We don't need the uniform dose in SBRT, and the results are good. The results are actually very good. You see, of course, there is now, this is a famous paper from 2011 that kinds of collect the new tolerance doses for SBRT, because they are really different even from the Quantec report. When you go to this very little fractions, you need the limits here. You see the limits in terms of volume and in terms of maximum dose. For many different organs. This is only the aorta and the bladder, but if you look at the paper, this is done. I will give you the paper. This is done for every organ. Applications are many. For extreme, SBRT is also called SABR, stereotactic ablative radiotherapy. Is very much used for the stage 1 non-small cell lung cancer. Stage 1 is a T1 and 0 and 0. T is the size, you know, that probably you know already because it's very much used, unfortunately. T is the size. So T1 means less than 1 centimeter. So it's a very small one. N0 means that there are no lymph nodes involved. And M0 means that there are no metastases. Oligometastasis means there are small metastases, but not many, like 4 or 5, so you can destroy them. But now it's used for many, many applications. I mean, it's used for hepatocellular carcinoma, it's used for advanced tumors now in the lung, T2, T4, which is more than 3 centimeters. Localized tumors in kidney, in prostate, in pancreas, in adrenal gland, essentially everywhere. And you see it's very competitive to surgery for small tumors. So for small tumors, can replace completely the surgery. This is actually a paper from a famous surgeon that essentially argues that if you have a stage 1 lung cancer, you don't need surgery. You better do SBRT. You get the same results. And you see attempts, this is from the Sloan Kettering, which is one of the most famous cancer hospitals in the world, together with the MD Anderson in Houston. Sloan Kettering is in New York. They tried to push to more extreme hyperfractionation. This is now from the hyperfractionation in 5 fractions here. These are extracranial metastases of renal cell carcinoma. The progression-free survival, this is a Kaplan-Meier plot that we will see, but essentially you see this means 100% progression-free survival, so the number of patients that have no progression. And then this drops as a function of, you see, in 2 years, you only have 20% of the patients where the disease is not progressing. But if you give single dose, and also if you give single doses of less than 24 gray, same. But if you give single doses of 24 gray, then you get 90% of progression-free survival. Very surprising. You see, that's an analysis in the Lancet Oncology a few years ago, stating that SBRT results in a high rate of control of metastasis, 80%. Around 20% of the patients remain free of progression at 2-3 years after treatment, low toxicity. SBRT should be considered in those with oligometastasis, especially if disease-free interval is more than 6 months. And of course, randomized trial, where you essentially randomize the patient into different arms, are always necessary to see if you improve also overall survival, not only progression-free survival. Now, why, especially these results, you know, trigger a strange conclusion, say why there seems to be a sort of threshold in the dose, you know, like above a certain dose, you get a much better result when you give single fractions. Many people, especially in the Sloan Kettering, is a paper from a few years ago from the Sloan Kettering, hypothesized that there is a new mechanism here. So that instead of using the usual mechanism when you have radiation exposure, stem cell DNA damage, stem cell DNA damage repair, failure of the DNA damage repair, stem cell death, and then you essentially kill the tumor, you go through another pathway where you have cell death signals, endothelial cell apoptosis, and microvascular dysfunction. This inhibits DNA repair, and then you go into the death. So essentially, you hypothesize here that you are damaging the vasculature of the tumor, not killing the cells, but you damage the blood vessels around the tumor with a sort of threshold, you know, at a given dose where you really cut them, and then you starve your tumor. At that time, the tumor becomes radiosensitive. You know, there is even an idea here where if you have hypoxic and oxic cells, you see, this will be the survival curve in A is the survival curve this dotted line is the survival curve of the oxic cells. Hypoxic cells are more radioresistant, of course. So the overall curve will be, here is dominated by the oxic, here is dominated by the hypoxic. But then if you have vascular damage, you have after a certain dose, you can have vascular damage, and then the curves drops again. And when you reach a dose of 24 gray or so, you are now in the region where you kill all the stem cells and then you sterilize the tumor. That's pretty much the idea. Completely new concept, completely new biology. It goes completely away from the concept we saw last time, you remember, of kill one cell at the first fraction, kill another cell at the second fraction, and so on and so forth. But is this true? There's another paper coming, more recent, coming from Columbia University in New York, where essentially they looked at the BD, they just calculated the BD, as you can do, for different trials for stage 1 non-small cell lung cancer, including 3D CRT, where you don't hypofractionate, you have long fractionation. And then for normal hypofractionation, let's say moderate hypofractionation, 3 to 8 fractions, and then extreme hypofractionation, like 1 fraction. Now, if you calculate the BD and you plot the tumor control, the TCP, as a function of the BD, you see that all the points stay in a very nice curve. So there seems to be no reason to look for new biology. It's only that with SBRT, you increase the BD. And if you increase the BD, you will increase the TCP. It's in the formula if you want. No, it's mathematical. So there's still a very heated debate here on whether there is a new biology behind SBRT, or you can actually use the simple alpha beta model. The linear quadratic model works perfectly. There are a couple of problems, still. Not so much repopulation. Repopulation, of course, gets better with SBRT. And repair can be a problem because, of course, if you want to give very high dose, you have very long treatment times. But these days with flattening filter-free machines, where essentially you remove the filter in the machine that makes the field flat. You have, again, a non-homogeneous field, which is a bit worse, but much faster. You don't have a problem with repair. For sure, you have a problem with the oxygenation. So we saw that one of the main points in fractionation is the reoxygenation. If you have very little fractions, or if you have even no fractions, I mean, only 1 fraction, then it's very difficult to imagine how can you kill hypoxic tumors where the OER can be as high as 3. How can you kill them? And you see, that's why you see this model is interesting here, because this would explain that you can kill them if you damage the vasculature of the tumor. Okay. Another problem, though, of the linear quadratic model is that it is nice, of course, we have seen, I mean, it can reproduce even this SBRT data, but the linear quadratic model is a low dose approximation, because the linear quadratic bends over all the time, It's a beta. So the tendency of the curve will be to bend over, but this is not what is observed experimentally. What is observed experimentally is that after a certain threshold dose dt, the linear quadratic curve becomes linear. Of course, when I say linear, I mean exponential. So which curve can be used in that case to calculate, the dose in SBRT? One of the simplest way to do is in this paper, where they propose a mixed model, which is a combination of the linear quadratic and you see here, you recognize it, the multi-target model. So the multi-target model will give you a purely exponential curve with an interception up here, of course. So this is now the purely exponential described from here for a dose higher than the threshold dose. So, and this is for the survival curve, and this is for the BED. So using the combination of the linear quadratic and and target theory here, you can have a curve that reproduces nicely the data. Also the data here, this is the total dose versus the equivalent dose, and there are some data showing that these predictions are correct. The last point here is the second cancers. Sorry, last point I wanted to touch is the second cancers, and why is that? This is important, especially important for the young patients, let's say, but not only for the young patients. We will see in a second why. Cancer survivors now are increasing. We have seen it. They are increasing because the cure gets better and better. So we are now in the US population, is 3.5% of the US population is cancer survivors, a lot of people. Now, the second primary malignancies in a high-risk group accounts for 16% of all cancers. So 16% of the cancers are second primary malignancies in previously cured patients. Or cured normally means that you have 5 years without cancers. There are generally 3 causes for this very high incidence, you see, of the cancers. 16% corresponds to only 3.5%. One is continuing lifestyle. For example, you are a smoker and you keep smoking. So of course, I mean, you are at higher risk than the rest of the population. Second is the genetic predisposition. So in many cases, you have a genetic predisposition to cancer. So first you get one cancer, and then you will get another cancer, and so on and so forth. And third is the treatment of the primary cancer. So because of the treatment of primary cancer, especially radiotherapy in this case, you get the second cancer, because radiation can also induce tumors. Assessment is difficult, of course, to see what is the cause, but a good point is those cancers like prostate and cervix, where you can compare with patients undergoing surgery, where you don't expect that surgery will increase the risk of cancer, even though this is also controversial. Too long to discuss, but there is a discussion. Another point can be Hodgkin's lymphoma, where the risk of breast cancer is pretty high, because in that case you irradiate essentially the chest, and the breast is very radiosensitive with a quite high probability of cancer, so you have a high risk of breast cancer. And also radiation-induced secondary cancers are mostly carcinomas, but a sarcoma in heavily irradiated sites are also observed. This is an example here of the relative risk of second cancer for prostate patients. So these are not young patients, these are relatively old patients. Relative risk radiotherapy versus surgery. You see that if you have more than 10 years, you have a significant, very significant increase in the relative risk, 30% of the, even though there are large error bars, of the patients undergoing radiotherapy versus surgery. And the second cancers, you see, surprisingly, I mean, there are cancers that are obviously like sarcomas in the field, rectum makes sense because you have the rectum in the field, bladder makes sense because you have the bladder in the field, colon makes sense, again, I mean, because you have the colon essentially in the field, but then you have a lot of lung cancers and a lot of sarcomas that are definitely out of the field. So that's a little bit more difficult to understand, but we will go into that. The problem is even more drastic for the pediatric patients for 2 reasons. The first reason comes from the risk as a function of the age. From Hiroshima and Nagasaki, it is known that the risk per sievert is higher if you are younger. And the second is just geometry. When you have irradiation, you have leaking, the stray radiation, which is radiation which is leaking, not going straight, but going in this direction. This is a relatively small problem when you have an adult, but when you have a pediatric patient, this means that you practically irradiate almost the whole patient with stray radiation. So you can also have a lot of out-of-field tumors. The best cohort here is the so-called CCS, which is a cancer survivor cohort studied at St. Jude. And you see here examples of the relative risk for central nervous system second cancers and thyroid second cancers. And this is again an example of the analysis of second malignancies after modern radiotherapy versus prostatectomy for localized prostate cancer. This study, you see, these are patients treated, this is the proportion free from all second malignancies for surgery and for conformal radiotherapy. You see that those with conformal radiotherapy are much worse than those with surgery. But if you take brachytherapy, actually brachytherapy that you know is not teletherapy, so you don't go through the normal tissue, is actually doing even better than surgery. This is one of the data that makes you think that maybe surgery is not completely innocent in terms of inducing second cancers. And the reasons are also biologically quite clear. This is a study on lymphoma. As I told you, lymphoma is a typical case cited because you have a fairly high risk of second cancer, essentially breast for women and lung for men. This is now a study of the overall risk. And what is said, if you want, is that if you take this is any subsequent malignant neoplasm, this is any subsequent solid malignant neoplasm. If you look at the risk, the incidence as a function of the age, going from the very old data from the 60s and the 70s to the much more modern data of the end of the 20th century, there's no improvement. You see, the red curve is always essentially the same. It's even worse, a little bit worse than the old data with 3D CRT. So this is really disappointing. In fact, the New England Journal of Medicine made an editorial saying second cancer of treatment for Hodgkin's lymphoma, continuing cause of concern. And this is, finally, we will go back to why is that. I mean, the reason you can imagine, because you have a lot of integral dose. So the modern technique we have seen in the treatment planning does not improve the integral dose, actually make it worse sometimes. So you cannot expect an improvement with IMRT compared to 3D CRT. Finally, just a reminder about the cause of the cancer, I mean, which is more for radiation biophysics, but just to remember, it's not only the initiation, so the mutations, if you want, that matters, but also especially the promotion. Promotion is very important, of course. This is the dose response curve that we know very well in the Hiroshima region, but we don't know very well in low dose and high dose regions. And also the dependence from the age is not always true that you have a large increase in the young cohort, or better said, you always have, it's always higher when you take the children. But there is also an increase in the middle age for many cancers, like lung cancer, you see, and bladder cancer, not so much for breast cancer. This increase is due to the inflammation, so to the inflammatory action, so to the promotions in this case, not to the initiation. And finally, the role of genetic predisposition, that this is a slide that I already showed in the radiation biophysics course, so I think this year many of you already know, but this is the famous ringworm, the Tinea capitis study in Israel that shows an amazing result on the predisposition, genetic predisposition for cancer. the very final topic that I want to touch again is whether we will need radiotherapy in the future because of the introduction of immunotherapy. Because immunotherapy, you see it here, how the immune cells, these are natural killer cells, lymphocytes that kill cancer cells. So the immune cell, the immune therapy, in the immune system, in principle, this is now a natural killer cell destroying a cell infected by virus. So that's more for COVID if you want. But that's to show you how it works essentially. Okay, you can watch the movie. What I want to say is that now with the Nobel Prize a couple of years ago was given to the inventors of the checkpoint inhibitors, CTLA-4 and PD-1. CTLA-4 is a checkpoint inhibitor between the T cells and dendritic cells that are those that create the lymphocytes that attack the tumor. The PD pathway instead is a pathway that the tumor cells use to stop the aggression of the T cells. So if you interfere with this pathway, you will have a better aggression of the tumor cells. And this is actually very effective for some tumors. For example, for melanoma, this is a case of a patient with melanoma, metastatic, very metastatic, very metastatic melanoma, treatment with ipilimumab, which is an anti-CTLA-4, and you see that it is completely free of tumor. The results, though, unfortunately, don't apply to all patients. You see, this is a long study with ipilimumab that shows that about 20% of the patients respond. You get better results now with anti-PD-1 or combination of anti-CTLA-4 and anti-PD-1. These are different trials, you see, where the bar is going up. To increase furthermore the bar, you can think of using chemotherapy, targeted therapy, or in fact, at the end, radiotherapy. Why radiotherapy? Because radiotherapy is actually naturally a vaccine. So when you irradiate the cells, the dead cells actually produce molecules like calreticulin, HMGB1 that are stimulatory for the dendritic cells to be activated and to produce cytotoxic lymphocytes that will kill the tumor. But unfortunately also produce suppressive signals like TGF-beta and CSF1 and Treg that essentially block this activation. So if we can use immunotherapy to reduce these signals, the combination of radiotherapy and immunotherapy can be brilliant. And in fact, this was observed, the first report of this combination dates back in 2012, when in Stanford, in Sloan Kettering, it was also studied in Stanford. In Sloan Kettering, they showed the combination of radiotherapy for one target, but then they show abscopal, this is called abscopal effect, when it is distal regression in lymph nodes in combination with the ipilimumab, which is an anti-CTLA-4. And now this is a more recent, is the Pacific trial. This is not a metastatic tumor. This is interesting. This is a advanced lung cancer, stage 3 inoperable lung cancer. And these results are very exciting because they show, you see, these results essentially changed the clinical practice for lung cancer by one day to another in 2017, so a few years ago, because they clearly showed, you see, that the patient with placebo have a much lower progression-free survival than the patient taking durvalumab, which is an anti-PD-1. And interestingly, it was also shown, you see it here, that the most important parameter to determine the success of the treatment was the PD-L1 status. So the tumor has to express the PD-1 so that this is effective. Not all of them, unfortunately, express the PD-1. But for those tumors that express the PD-1, the durvalumab was effective, which makes perfectly sense in a way. So you see, this is now a hazard ratio. We will discuss medical statistics later in the course, so you will understand better this kind of plots. And this is another trial now in radiotherapy in combination with lung cancer using CTLA-4. This is interesting because this trial was used for patients that were treated already with immunotherapy and radiotherapy alone. Now they were treated with treatment of one single metastasis, you see, with the fractionated scheme, hypofractionated scheme, only 3 or 5 fractions, 9.5 or 6 gray, and then ipilimumab. And you see that in about 30% of the patients, you have either complete regression, partial regression, or stable disease. These are 70% of the patients are in progression, but these patients are 30% of the patients, this treatment was very effective. This concludes the lecture for today. Thank you very much.